So checking transistors at an ohmmeter with an ohmmeter. And if you know how to check a diode, you can check a transistor. And that's all there is to it. A lot of people call it the diode scale on the meter. I like to call it a p-n junction scale. So we can use this same scale on our meter to check any p-n junction. Let's see if it's going to focus in. So here's our p-n junction scale on this meter. And of course, so anything that's got a p-n junction, we can check it with this scale right here. And we know that if we get across a silicon junction and we forward bias it, we're going to read about 0.7 of a volt, right? If we get across if we reverse bias it, most meters show overload. So if you think about a transistor like this, now it's not really like this, but if you think about it like this, then what we have is we have junctions that look like this. So if it's an NPN transistor, and if you could think of it like this, and this right here might be the emitter, and this right here might be the collector, and this right here would be base. You should see how we can check this. So what I would do, I would put my positive lead right here, my red lead right there, and then I would touch this lead, and I should read about 0.7 of a volt. And then I'd move my black lead up there and touch it, and then I would measure about 0.7 of a volt. Then what we normally do is we swap it around to make sure the thing's not leaky. So we swap it around, and it should measure what? It should measure an overload. Then what we do is we come over here and we check across the emitter collector, and you're never going to forward bias two junctions there, right? You understand? So you should measure an overload across the emitter collector junction. So you need to check those just to see if the transistor is leaking. And we're going to show y'all how to identify an actual transistor, a BJT. We don't know if it's an NPN, and we have no idea what it's a NPN or a PNP. And I'll show you something that I've learned over time. You won't find this in a book, or you won't find it on the internet. And I went and tried to figure out somebody. You can identify an NPN and a PNP, and you can identify the base, but you can't. People don't tell you how to identify the difference between the emitter and collector. So the test BJT is similar to diode. We select the p-n junction scale on our digital multimeter. In the forward bias and NPN, we put our positive lead on, we put our red lead on the base, and then we touch the collector and we touch the emitter, right? You understand? And it should measure about 0.7 of a volt both ways. If it don't, if it measures 0.3 or it measures 0 or it measures an overload, then it means that the guy's what? It's bad. Okay, you understand that? If it measures about 0.7 of a volt, it don't necessarily mean it's good, but at least it's got a chance of being good. And then what we'll do is we'll double check reverse bias to make sure the thing is not leaking. So it should measure overload reverse bias, and it should measure good and forward bias. And then, of course, we do exactly the same thing with the PNP. Well, what do? We just instead of putting the black lead on the base, the red lead on the base, we put the what? We put the black lead on the base. If it's a germanium transistor, it's going to measure around 0.3 of a volt. If it's a silicon transistor, it should measure about 0.7 of a volt, and that's good. So this transistor, I know what it is. This is a 2N3904. So if we know what the transistor is, then what we can do is we can go and we can look this transistor up on the internet, right? Of course, we won't go to the internet. We can go to Blackboard because all these transistors that we use in lab are posted there. But literally, all you'd have to do is just type in 2N, 2N3904. These are JEDEC registered packages or JEDEC registered transistors. And what that means is anybody, and it's open technology, which means anybody can make a 2N3904. So what I'm saying is you might not run into a transistor that starts off with what? 2N. It's just if it's JEDEC registered, it'll start off with 2N. But you can just come up here and type in like 2N 3904, and what I usually put is PDF because that's a professional document file, and then it'll pop up, and then it should be available. Now be careful, just because it says PDF, look at your actual link. You want your link to end with what? PDF, because there's a lot of companies that pop that up there, and what they're trying to do is they'll give it to you, but for a price. So you got to create a login account and all that kind of stuff. And odds are these guys here are going to be up there somewhere. So this is the 2N3904, and then we need to figure out what the pinout is. So the term pinout, we use that to pinout is what shows you what signals are assigned to each pin, right? Does that make sense? So when we look at this, it says my emitter is assigned what? Pin 1. My base is assigned pin 2. And my collector is assigned pin 3. Now this is a transistor outline, TO92. Now the TO92 does not mean your base is going to be in the center. It just means it's going to be shaped exactly like this. All TO92 cases are going to have the same shape. We can get TO92s and SCRs. We can get them in triacs, which are not even transistors. FETs can be in a TO92 case. Voltage regulators can be in a TO92 case, so it could actually be an integrated circuit. So don't take for granted when you see these little TO92 cases that these guys here are transistors. So any solid state device that will fit in a 3-pin package could be in a TO92 case, and it's not high current. These guys are not very high currents. I think I can't remember what this one's rated at. We can look real quick. I should know that. So this guy maximum current is 200 milliamps, which in the name of things is not very much, right? So we wouldn't use these guys to drive a big speaker. But we could use it to drive another transistor that drives a big speaker, right? So normally when we go from very, very low power to very, very high power, we go through amplification stages. We have one stage that'll give us a certain gain and do this and do that, and then we'll go up, and at the end we come up with something that's going to provide us with a lot of power. So this is a TO92 case, and that's a pretty good picture, but it's a little tiny thing. So this is my finger, if I can get it inside the picture. Undoubtedly I'm zoomed. Let's see, I want to turn. There we go. So I'll come up here and wherever I'm at. Now it's not showing it all. Mislaid pads, right? Okay, here it is. Where am I at? Something just don't make sense. I don't know why it's focusing over here yet. So here's a little TO92 case. And you see it's in the shape of a D. And notice when you look at the pinout, we reference this from the top side, from the flat side. So on this one, this pin right here would be the emitter. This pin would be the base, and this pin would be the collector. I hope I put that back in the right place. So I got my meter so we can see it. I've got it on the diode scale. And so what I'll do is I'll come in and I'll take my black lead and I'll put it on the base. And then I'm going to come over here and touch it to the emitter. Just touch it to the emitter ridge. And it's measuring 0.705. Now I want you to notice something. You're not going to find this in a book. 0.705. Okay, now I'm going to come over and put it on the collector. What does it measure? So what did you notice? Here's the emitter. Here's the collector. So what did you notice about the emitter? slightly more. And you're going to find that's true. So what we're going to do here in a little while is we're going to show you how not only can we figure out what type of transistor it is, an unknown transistor. Not only can we figure out whether it's an NPN or a PNP, we can also figure out which lead is the emitter. But once I identify the base, we'll notice that the emitter measures larger, slightly larger, not a lot larger, slightly larger than the collector. So what I'll do next is I'm going to reverse bias it to see if it's okay. So now I've got my negative on my base. That measures overload, and then I'm going to measure collector to emitter, and that makes no difference, and it measures overload. So my collector to emitter measures overload. The polarity don't make there because you can never forward bias that going across, and then of course base to collector and base to emitter, we check that, so this transistor is good. And it's a PNP, right? You understand that? If I had an NPN transistor, and undoubtedly I got these things mixed up, guys, so y'all have to look at them. So this is a I just messed up the end. This is a 2N3906. Now, the 2N3904 and the 2N3906 is what we call a complementary pair. So usually in electronics, when we say complementary, we don't mean we're saying, oh, you look good today. What we mean in electronics is if it's complementary, it means it's just opposite. So it means the 3904 and the 3906 are complementary pairs. It means they have the same specifications, but one is a PNP and one of them is NPN. And later on, we'll see when it's required, when we work these things together, where we have to use complementary pairs. So now I'm going to come up here and I'm going to put my black lead on my base, and I'm going to put my red lead on my emitter. Notice it's measuring 0.72. I'm going to go over to the collector, and it's measuring 0.715. So 0.72 on the emitter, 0.715 on the collector. So notice the emitter measures what? Slightly more, because it's heavily doped. It's got a lot more majority carriers in there. So its barrier is going to be its depletion region is going to be a little more. Your collector is moderately doped, so it don't have as many free electrons in it as the emitter does. And that's why we get a lower barrier voltage on our base to collector than we do on our base to emitter. So what I'm going to do now is, and we have cases, you have some of your what we call transistor outlines are in your book. What page is that on? So this is in chapter, 9? Where we get a basic introduction to this, and we get into saturated switch, so we started talking about that. And then some of your transistor outlines are on page 218. Now this is not a lot of them. In fact, they don't even show the TO92 case. So what I've done on Blackboard is I put a little better outline on there. And you can look up transistor outlines on the internet and probably even get more. But these are the basic ones. And it should be on Blackboard. And then it could be in our class, solid state. And then it's going to be in data sheets. Reference material. And these are what we call transistor outlines. Where's it at? Transfer text, formula sheet, standard resistor, outline package. And I'm sorry this guy came up, but this is the TO92. So bring that up on your on Blackboard. Let me go get some more transistors and see if y'all can figure out what packages they are. I don't see a TL 46. What do you see a TL 46? So which row would it be and which column would it be? This column right here from the left, or this column right here? This column right here? Could be. Could be. But notice how squatty this one is. We don't have any of these. But see the height right there? This is probably more likely a TO39. But but see how narrow the little path was? Now the package don't give you the pin out. Then we have this guy right here. This should be obvious. These are high current transistors. These are probably the biggest package that you'll see before we go to the other type. Okay. We got this guy right here if I can find it. Now what's so strange is when we look at the bottom, it's only got 2 leads. So what package is this? This is a TL3 pack. Well, how can it only have 2 leads? Well, the whole shell itself is one of your leads. And which lead would the shell be? Which one is going to get the hottest? Which one do you want to get? Which one do you want to give the most exposure to the atmosphere? Huh? No, y'all, we just got through talking about it, guys. The emitter base drops 0.7 of a volt. The base to collector is reverse bias. So the base to collector always drops a voltage if the transistor is not saturated. And anytime I push a current through a voltage, it creates heat. So which junction gets the hottest? The collector junction. The collector lead gets the hottest. So that means on this one, this whole outside shell right here is the collector lead. Which makes it easy. So on this one, if I wanted to figure out which one was the base, if I don't keep dropping it, guys. The problem is when I drop it, it goes under the table. So if I want to figure this one out, then I'll just come up here. I know the outside is the watt, the collector. So now all I got to do is identify the base. So I'll come up here and just touch the 2 leads. And I'll touch it right there. It measures nothing. So I'm going to come up here and I'm going to swap it around. I'm going to put it right here. Okay. And so here's the collector. 0.489. Here's the emitter. 0.524. Now you notice the emitter measures what? More. So what we did is we identified this. I've got my positive on my base. And then I got my negative on the collector and the emitter. So this would be an NPN transistor. And we can look this up. This is a 2N6752. But this guy right here is going to be rated in amps. These guys are not going to be rated in milliamps. These guys will be rated in amps. This is its cousin right here. So here go. We'll get it first. And I'll go ahead and let you see it too. This is its cousin right here. Oops. This looks the same, but it's smaller. So what case is this? Is this in that outline? Y'all got it, I don't know. So what case is this? It's smaller, same version as the TO3, same layout. So the metal is the collector. So what case is this? Is it in there? This is a TO220. And you're right, I don't fit TO220. So y'all didn't have a shot at that one. Y'all do have a shot Let's see if this one's in there. Don't see this one in there either. I don't see this one in there either, I don't think. So we need a better one than this one. I don't see this one either. So I need a better one. This one. I do see this one. It's a little different, but I think it's the same one. So of course, the bigger the transistor, what would the bigness of the transistor mean? What do you think that would, what would that be relative to? So the bigger the transistor, what do you think that would mean? Huh? Huh? So what type of valves are these? What are they controlling? No, they're not. What type of valve are they? What are they controlling? They generate. They get hot. You know, anything that's conducted. What are they? They're valves. What are they valve? What are they opening? Huh? No, they have nothing to do with voltage. These are current valves. These guys are current valves. And it's just like, because that's what's flowing, right? You understand? So if I said, what does a valve have on a water line? Water line, what does it control? You wouldn't say it controls the pressure. You'd say, well, it controls the what? Flow. When I'm in the shower, I want it to be stronger. What do? I turn up the flow. I don't turn up the pressure. I turn up the flow, right? You understand? So what are these guys? What do transistors do? What kind of valves are they? They are current valves, right? You understand? Now we can get a voltage by running them through a resistor, but it's not the transistor giving us the voltage. It's the transistor changing the current, and then the voltage drop across the fixed resistor is what's developing a voltage drop, right? You understand? So these are current valves. That's what there's. Voltage does not flow. Y'all understand that? The voltage source does not move. So the voltage is the source of the pressure. Now we can have a loss in pressure, but the pressure itself is not moving, right? You understand? So what's moving? Current. So let's see if we can identify the leads on this thing. So to identify the leads, what I'm going to do is I'm just going to randomly choose a lead. Okay. So I'm going to come up here, and normally what I do is I start off, this is just me, I usually start off on the right, and I put my red lead on there, and then I touch the other two leads. And I see nothing. Y'all see that? Yes or no? Okay, can y'all see what I'm doing? I know I'm blocking it. I touch this lead, I touch this lead, and I see nothing. So what am I going to do? I'm going to switch the red and the black lead, and I'm going to touch this side right here, and I'm going to touch this, and I see something, and then I touch this, I see something. So I just found the base. So that means the base is on this side. So that's the base. This was measuring 0.525. This is measuring 0.534. So the emitter is on this side over here. This is the base. This is the collector. This is the emitter. Now on this one, I can kind of cheat in that I can touch the center lead. What's the collector? And I can touch the tab. Because the tab is the collector, right? You understand? Because that's the lead that produces the most heat, because that is the junction that is reverse bias. So all your voltage drop is in the collector junction, or in the collector semiconductor, because that's the guy that's dropping the voltage, right? You understand? Let's see if we can find another transistor that's not identified and see if we can figure out the leads on that one. This is an ECG transistor. No telling what this is. Sylvania was a real neat company. They finally went under. Sylvania's still out there, but their semiconductor division is no longer. I don't think they are. And they used to make cross-reference transistors, which meant that if you couldn't find your transistor, you could look at a cross-reference number and you could buy an ECG equivalent to that, which means they guaranteed that it met or exceeded the specifications for the device you want to do. So I'm going to come over and do the same thing. I'm going to put my red lead here, and I'm going to touch the other two leads. Okay, then I saw nothing. Then what I'm going to do, I'm going to swap them around, put my black lead on my selected. I'm going to touch there. I don't see anything. Here, I don't see anything. Then I do this again. Touch here, here. I'm going to touch here and here. So there we go. So when I touch here, I got my positive right here. When I touch right here, I see an open. When I touch right here, I see 0.6 of a volt. So what does that mean? That means this guy over here on the left, I know I'm blocking y'all guys. I don't know how else to do this. So what I'm doing is I'm putting my red lead right here. Then I'm touching the center. And I got an overload. I touch this lead over here and I get a junction. So what that means is this lead on the right is a PN junction. Okay. So what I'm going to do now is I'm going to leave that and I'm going to come over and touch this guy right here and I measure 0.6 of a volt. I touch this guy right here and I measure 0.6 of a volt. So what does that mean? So y'all see how I did that, yes or no? So first of all, I start with just a random lead. Okay. Let's say I start with the black lead. It's up to you. And then I touch the other two leads. If I don't get any measurements, I come over here and swap them around. So I'm going to put the red lead right here. Okay. I put the red lead right here. And I touch the black lead to this one. I get nothing. I touch the black lead to the center one. I get nothing. I touch the black lead over here to the right and I get a junction. Well, what that means is this guy on the right is the what? Is the base. So now I'm going to just leave that guy alone and then I'm going to come over here and look at this one. So this is measuring 6.66 or 664 millivolts. This guy right here is measuring 670 millivolts. So on this one, the base is on the right, the collector's in the middle, and the emitter's on the left. Wasn't that right? But they're the same package. I was watching a video today, and a guy said, well, this is a 3904. It's in a TO92 case. It means the base is on the emitter, and it says now all TO90, and it's going to be the same for all of them. That's what he said. So what did I do right off the bat? I turned that sucker off. Because we just proved that different. In fact, if you see a TO92 case and you measure it and it appears to be bad, it doesn't mean it's bad. It just might not be a bipolar transistor. It could be an SCR. It could be a triac. Any device that requires 3 leads can sit in a TO92 case. It's just that it's not going to have a lot of current to it, right? You understand? It could be an integrated circuit. Like I said, a voltage regulator only requires 3 leads. It requires an unregulated in, it requires a regulated out, and it requires a common or an adjust lead. Since it only requires anything. So this right here could be a transistor. This could be a integrated circuit. This could be an SCR. This could be any electronic device that requires 3 leads. Everybody understand that? So if you see that's a good test question. If you see a device that's got 3 leads on it, will it always be a transistor? Would that be true or false? It's going to be false, right? Y'all understand that? So these are bipolar transistors. And of course, the next chapter we'll look at, and we're going to be in lab, the next lab we're going to do is we're going to let you check these things. So no matter what lab you're on, I want y'all to do, kind of like when we check the diode, I want y'all to go ahead and skip and do what? Do this lab. Okay, so y'all going to check transistors. What we have, the way the thing is written up, is we got two transistors. We got a 2N3906 and a 2N3904. Guys, you're going to have to look at that because I popped one of them in the wrong side. There's supposed to be 8 in each side. So y'all look at it when y'all pull them out. When y'all put them back in there, I want the 2N3904s on the left, and then the 23906s on the right. And then what we have is we have two transistors. One of them's labeled 1 and one of them's labeled 2. And what you're going to do is you're going to determine what type of transistor it is, or the PNP or an NPN, and whether it's good or bad. And one of your unknowns is bad. Okay? Y'all understand that? And so you can see, by the way, if a transistor checks good in circuit, and this is true, if you've got a solid state device that checks good in circuit, we assume it's good. If we checks bad in circuit, then what we do is we pull out at least one lead and check it that way. Because anytime, anything that's in, y'all understand parallel circuits, right? So if you got anything in parallel with the transistor, you might be measuring what's in parallel, right? You understand? When we get into amplifiers, you're going to have a lot of resistors and stuff in there. You know, so if it checks good in circuit, we assume it's good, right? If it checks bad in circuit, then we isolate it and check it again. Are you okay? All right, guys.